Dear participants, I would like to invite Professor Dr. Vesselin Drensky from Bulgarian Academy of Sciences in Bulgaria. It's a great pleasure for all of us to have here Professor Drensky for the valuable talk on non-finitely based and limit varieties of algebraic systems. Professor Drensky, you are welcome to do your presentation, please.
Thank you very much. Let me share the screen.
Yes, you may start, please.
It's okay now?
Yes, it's okay.
Okay. First of all, thank you very much for the invitation to give a talk.
Sorry, Professor, could you please share your screen, full screen?
Yeah, sure. Now it's okay?
No, we can hardly see your screen.
But this is full screen now.
Okay, please go ahead.
Sorry, you can try to click Ctrl-L.
Yeah, I already had Ctrl-L.
Oh, okay, it's perfect.
Okay, thank you very much. First of all, since of course, I'm very grateful to present this talk. Although I have a long time cooperation with the young Turkish mathematician Sheikh van Dijk from Adana. So he spent 2 years in Bulgaria, and we still work together. And since I give some references in the talk, the best way to see this is simply to ask me by mail. Here is my email to send the presentation, or if the organizers have the presentations posted, I'll send them to post the presentation. So if ask a person which are the main problems in the algebra, very naively you should answer, describe all groups, all semi-groups, all rings, all algebras over a field, associative, non-associative. But of course, this is a hopeless problem. So we need something else. And there are two obvious approaches. One of them is the structure approach, and the other is the combinatorial approach. For example, the algebraists, even the master students, they know that the finite dimensional associative algebras, they have a good structure. They have the Jacobson radical, which is nilpotent. Modulo the radical, you have an algebra which is semi-simple. Every semi-simple is a direct sum of simple algebras. You know which are the finite dimensional simple algebras, etc., etc. So you have a good description of finite dimensional algebras. But what is the combinatorial approach? You divide the algebraic objects in classes. You call these classes varieties, depending on the defining relations which they satisfy. The good thing here is that you can do the same things for groups, for semi-groups, for rings, for algebras, commutative algebras, associative algebras, Lie, Jordan, etc. This idea is very old. It comes from the work by Gareth Birkhoff, Universal Algebras, and Bernard Neumann on groups. This is from the 1930s. And I'll speak about groups, but the same is for semi-groups, for associative rings, etc., etc. If you have a set X, then there is an algebraic group, algebraic system, for example, a group in the class of groups, which is generated by this set, and this has the universal property that if you send the set X to some algebra or to some group from the same class, you extend this uniquely to a homomorphism from the free object to the object you have chosen. You call this the free algebraic system in the class of algebras freely generated by this set. So we assume that X is a countable and infinite set, XD is a finite subset, and for the corresponding algebras, you write F of V or FD of V when you speak for the corresponding object. So, how this object look like? For example, for the class of all semigroups, you have simply all the words in the axis, and you multiply two words, simply writing him one after another. When you speak about monoid, you add also one to this set. If you have commutative semigroups, you simply have all the monomials in commuting variables. Something similar if you have groups, of course, you also allow the inverse of the elements. For the abelian groups, you simply have monomials with negative and positive degrees in the variables, etc. The same is for the free associative algebra. Here, over a field of for the free associative ring, you simply have linear combinations of such elements. And if you consider non-associative algebras or non-associative rings, you have a similar object, but you have also parentheses in the words. And what is a variety? So you take, for example, some group or semigroup, the class of groups or semigroups, and you take two words, and you say that U and V, you say that U equals V is an identity for an object. If you replace the variables by elements, you got an equality. And if you consider all the objects which satisfy a given system of identities, this is a variety defined by this system of identities. And of course, you speak about that one identity follows from other identities if it holds for all the cases when these identities hold. So there is a theorem by Birkhoff from the 30s, which states that a class is a variety if it is closed under three operations, taking homomorphic images, sub-objects, and Cartesian products. So if you have an algebra R or a group R, and you apply first Cartesian products, then you apply sub-object and homomorphic images, you get all the class of the varieties. So in this case, if you start from an algebra R, the variety generated by algebra R, these are all the elements, all the objects obtained in this way. Now, traditionally, here you have something which is different from linear algebra. You say that a set of identities is a basis of the variety of the identities if it is defined by this set of identities. And this is finitely based if you can define it by a finite number of identities. You don't ask about independence of the identities. You simply use this word basis for all the cases. And if you cannot define a variety with a finite number of identities, then you say that this is not finitely based or infinite based. And what is the finite basis problem? Is it possible to define any variety with a finite number of identities? Of course, you have a weaker version of this. If the variety satisfies some explicit given identity, can you be sure that this is defined by a finite number of identities? And of course, if not finitely based varieties exist, to give an explicit example. So in the sequel, we shall discuss only examples of infinite based varieties. There are also a lot of positive results, but we skip them. We speak only about infinite systems. So the first examples, they come in same groups from 1965, when Birukov proved that this system of identities here is not finitely based. And a little bit later, there is another example, also of semi-groups. But now, about 35 years ago, there was a survey article by Shevrin and Volkov, when they gave more than 40 examples of varieties of semi-groups which are not finitely based. And this number now increases. For the case of groups, the problem was asked by Bernard Neumann in 1937, and the first result was only in 1970 by Alexander Roshansky. He proved that there are continually many varieties of groups. And as a consequence, there are infinitely based varieties. And the first explicitly given examples were by Adyan. You know that Novikov and Adyan, they proved that the Berson, they gave a negative answer to the Berson problem, that if you have a group which is finitely generated and have given exponent, is this finite or not? And using this technique, Adyan gave an example of variety which is not finitely based for the case of groups. So these are the defining relations. You take the commutator of x in power Pn and y in power n, and you take everything in power n when P is prime. And in this case, you get a variety which is not finitely based. There is another example by Michael Vonley, which is also in 1970, which is much easier to understand because it doesn't use the complicated theory of Novikov and Adyan. And here are the identities which define this one. Here, when I speak about group commutators, they are left normed. So they are in this way. And the simplest examples, they are due to Yuri Kleiman in Russia and Roger Bryan in England. They prove that the so-called product of rise before A2 is not finitely based. This variety consists of groups which have a normal subgroup, which is a billion of exponent 2, and the factor group is of exponent 4. So this is the base of the identity. You have a product of squares in power 4, and you cannot remove all identities but finite number to get everything which you need. And for infinite based varieties in non-associative objects, there are simple examples which work in the same way for non-associative rings, non-associative algebra over any field. For binary magmas, so magma, this is a set with one binary operation. So these are the identities. This is almost obvious that you cannot remove any of this identity. And if you remove, you get something bigger. And the first example for varieties of Lie algebras, it was given by Michael Vonley in 1970. It was over a field of characteristic 2. This was the central bimetabelian variety defined by this identity, and a series of identities of this form. And it's proved that this is not finitely based. And Vorichenko, 10 years later, here there's misprinted CH, Vorichenko, he added to this system one more identity and obtained a variety which is locally finite. Locally finite means that the finitely generated algebras are finite dimensional, or finite when you speak about groups, for example. And if the field is infinite and of characteristic 2, then you have a very nice example, 2 by 2 matrices considered as Lie algebras. They have no finite base of the polynomial identities. This is in the same paper by Vonley. Then the explicit form of all identities, it was in my PhD thesis in Moscow in 1979. Lopatin 4 years ago, he found another proof. And the identities, yeah, this one, you have central immutable identities, the identity of only, and this identity here, a series of identities, where you have 1, 2, 3, 4, and you take cyclically 2, 3, and 4. 3, 4, 2, 4, 2, 3. These identities, they form a basis of the polynomial identities for 2x2 matrices over an infinite field of characteristic 2, considered as a Lie algebra. And also there is another example by von Lie, also for Lie algebra. This is a big and binary varieties of Lie algebras, again in characteristic 2. A big and binary of class 2, this means that if you have commutators of length 3, and you take 2 commutators, you get 0. And these are the identities which form a variety which is not variety based. You see here you have 1, 2, 2, 3, n minus 1, n, and 1. So you take cyclically all the elements from 1 to n. And of course, there is a natural problem. There is a simple 3-dimensional Lie algebra with the vector product. So this is an analog of the 3-dimensional vector space with the vector product. In characteristic 2, when the field is infinite, is the basis of this polynomial identities not finite. The problem is that if you consider a field of characteristic different from 2, 2x2 matrices and this algebra, they have a finite basis of the identities. So this is something which is, I believe that this is the case, but I'm not sure how to prove. I don't know how to prove it. And when the characteristic is positive, but bigger than 2, then I have a paper which shows that there is an infinite based variety. These Lie algebras, they are solvable of class 3. This is the solvability. They have some analog of the identities of only. And this result was obtained independently in the same time by Ulrich Kleiman, but it was not published. And also, if you add to this system this polynomial identity, if you multiply several times by x2, you get 0. Then you find a variety which is locally finite and still infinite based. And there is one more example. This is in the same paper, which I already had the first example. In characteristic P over infinite field, there exists a finite dimensional Lie algebra with infinite basis of its polynomial identities. And of course, there is a very difficult open problem. What happens in characteristic 0? Are all varieties of Lie algebra over a field characteristic 0 finitely based? For associative algebra, this is the answer is yes, but for Lie algebras, we don't know. And for associative algebras, this problem was asked in 1950 by Specht. Jürgen Specht, he is known in his results on representations of the symmetric group and also some other representation theory, but also he has one paper in ring theory. This paper, which is translated in English, this is walls in rings. The first part, he asked the problem about finitely based varieties for unitary associative algebra over a field characteristic 0. And this paper, all the branches of algebra that now you call the Specht problem, the problem about finitely based problems of any algebras, groups. And in the 1980s, Kemmer, he proved, he developed a structure theory of T ideals. This means ideals in polynomial algebras. And I'll mention only two consequences: that the polynomial identities of every finitely generated PI algebra means algebra with polynomial identity, are the same as the polynomial identities of some finite dimensional algebra. If the algebra is not finitely generated, then there is an analog, which is stated in find the affirmative answer to the Specht problem, that over a field characteristic 0, all polynomial identities of associative algebras follow from a finite number of identities. And in characteristic P, there are also a lot of examples. The first example was given by Belov in 1999, and almost in the same time there were two more examples by Grishin and Shigolev. It's amazing that these three persons, they participated in the same seminar, the seminar of Latishev. In the most seminars, they presented three different answers to the Specht problem in characteristic P. And these are the papers where they are given. But there is a very simple example in characteristic 2. This is by Gupta and Krasilnikov, Kantor Gupta and Alexei Krasilnikov. This is in 2002. These are the identities which, without finding base of the identities. And there is one more example, again in characteristic 2, again by Kantor Gupta and Krasilnikov, with this identity. So you can explain the proof maybe to a graduate student in algebra. Even the person is not a ring theoretist, but any kind of algebraist. And there is a conjecture that over a field of characteristic 2, an infinite field of characteristic 2, 2 by 2 matrices, they don't have a finite base of their polynomial identities. For algebra, this is the case, but we don't know what happens with associative algebras. But it would be nice to have such an example. And now there are also some positive results when we speak about finite objects. For example, if you finite Jordan algebra or finite rings of the same class, they have a finite base of their polynomial identities. For groups, it was Schultz and Powell in 1964. For associative rings, finite dimensional associative algebra over finite fields, it was Kruse and Wolf in the 70s. For Lie algebras, it was Bertoul and Olshansky. For Jordan algebras, it was Medvedev. So there was a lot of activity in the 1970s about this one. And they all used structure theory of groups and rings. But for Lie algebras, the proof involves also quasi-identities. Quasi-identities, if something happened, then something. Yeah. And also this is known that you have a finite critical object, so I don't want to describe what's a critical object. And the problem, this is the following. If you have a finite algebraic system with a finite system of operations, it is true that this is finitely based. It was asked by Birkhoff in 1948, and the first result needs directions for 2 elements. If the algebraic system consists of 2 elements, it was answered by Linden in 1951. And the comment of Linden was that it is perhaps surprising that this problem is not entirely trivial, even for algebras that contain only 2 elements. So, other examples, Linden, okay, he showed that if you have an algebraic system with 7 elements, and you have 0 and you have 1, and you have 0 and you have 1 binary operation, and you have table with that almost all elements are all the products are 0 except this one, then you have that some identities which cannot follow from each other, so that this system has not finite number of identities. Then, of course, you can go further and ask what happens, what is the minimal number of elements of a finite algebraic system without finite basis of the identities. For 3 and 4, when the object has 3 or 4 elements, there is an example by Vesselin when you have an element operation, 4 elements in the set. Even there is some set of identities which is okay, relatively nice. And finally, Mursky, he proved that there is a 3-element binary magma which is not finitely based. It consists, this is the multiplication table. And if you go further, the idea of the proof that Mursky showed that you have a system of identities depending on n variables, which don't follow from any system of identities in less than n variables. So for any step, you have to add new variables to get what you need. So you know that all these problems about finitely based problem, they have some logical aspect and also they have philosophical objects. Because if you can define something with a finite number of identities, from the point of view of philosophy, this is nice. If you cannot do this with finite, this is something which is not good. And if you translate the problems in the language of logic, you can ask, is there an algorithm which allows from finite algebraic objects as an input to determine the Turing machine. You can construct an algebra which is finite and the finite type such that the Turing machine stops if and only if the algebra has a finite base of these identities. But there are also some other results in this direction in the 60s, but I think that this problem is still open for finite semigroups. And if you consider semigroups with finite
I think there is some connection problem. Let's wait a couple of minutes.
I'm sorry, but I should start the. Can you see now?
Yes, yes, please.
Okay. I'm sorry, but
Don't worry.
in my home, the connection sometimes is very bad. So there is an example of finitely based. These matrices, they have only zeros and one. And if you consider semigroups of 5 elements or less, then Drensky asked the finitely based problem for such semigroups. And there were a lot of attempts for all these things. And it was shown that, for example, that every semigroup with less than 5 or less elements has a finite base of these identities. So if you have an infinite system of independent identities, so this means that you cannot remove any identities to have the same things, then you have a finite continuum of subvarieties. For 6 element same groups, something strange happens here. So there are semi-groups which have an infinite base of identities, or they have a finite number of identities. So there, when we speak about 6 element semigroups. So this is something which is Trachtman here has a result that if you have a 6 element semigroups, it generates a varieties with continuum subvarieties. The same was, another example was but Edmonds, Lee, and Lee, much later. And if you consider semigroups with 5 elements, and all they generate varieties with finite number of subvarieties or count many subvarieties. There is only one exception. We don't know what happens with this semigroup with 5 elements. How many subvarieties it has. And I already mentioned that there was a paper by Chevron and Volkov in the 1980s, and now there is also a more newer papers when they study such questions for varieties. So I showed 2 exotic examples. One of them, you have varieties of same groups. So, base, but if you consider involution of same, is not finite based. And now, when you speak about finite rings and finite dimensional algebras, the first counterexample of a finite non-associative algebra without finite basis of identities, it was given by Pauling in 1970s. To multiply from the left, you get 0. And there was an improvement of this example. This is by Wolf, who started with a 2-dimensional vector space and added 2x2 matrices, such that the multiplication is that all the products are 0 except when you multiply a vector and act on the vector with a matrix. Then again, this algebra satisfies a left nilpotency, and it has no finite base of its identity. This idea was further developed of this kind. For example, Maltsev and Parfenov, Yuri Maltsev and Parfenov, they did this in characteristic 0. The algebra was 5-dimensional again, but the vector space it had an action with 2x2 upper triangular matrices. This algebra has a basis of polynomial identities, which are this one. Here again, the products, they are left normed. And when you consider a positive characteristic of a finite field over an arbitrary finite field, you have papers by Isaev and Kesizin. You have also a 4-dimensional algebra with infinite base of the identities, over any field. This is a little bit similar. You have a two-dimensional vector space acting with two matrices. So it was done 5 years ago in 1950. But all these experiments use the notion of weak polynomial identities. So you have an associative algebra or non-associative. F is a weak polynomial identity for the pair RV if it vanishes in R when you replace the variables with elements from B. Of course, you can consider the same for free associative algebras when this algebra R is associative. And further, we shall discuss what happens only in the case of associative algebras. So the weak polynomial identities, they were introduced by Razmissov to solve two important problems. The first one was to give the polynomial identities for 2 by 2 matrices, both associative and Lie characteristic 0. And also to construct central polynomials for matrices of any size. The central polynomials, it was the existence of central polynomials, it was one of the central polynomials in ring theory, and it was solved independently by Razmissov and Formanek, by Formanek in 1972, in Razmissov in 1973. And depending whether you start an arbitrary subspace V, or this which generates R, or V is a Lie algebra, or it's a Jordan algebra, then you can consider different consequences for the identities, depending on the structure of algebra. And there are many applications of polynomial identities. For example, Vonley constructing infinite-based varieties of Lie algebras in characteristic 2. In practice, he showed, although he didn't state it explicitly, that if you take commutator of length 3 and this system of identities, weak identities, this has not finite base of identities. Something similar happened with Bolichenko in characteristic 0. He showed that this variety is finitely based, but the key moment was again that if you consider weak polynomial identities satisfying this identity, commutator of length 3, this has no finite base of the identities. And of course, you have a problem. What happens in the case of positive characteristic bigger than 2? If you give an example, then you have an infinite based varieties, which is subvariety of the variety of nilpotent, big and by nilpotent of class 2 algebras. And also there are some other examples, so I don't want to discuss. So probably when you consider varieties weak polynomial identities, this is natural to consider also varieties of group representations. So you start with the free group, and you consider the group algebra over a field. So if you have a group G and you have a G module, then you say that you have an identity in the pair GM, where G is the group, M is the module. If you take this polynomial and you replace the elements by elements from the group, acting on M, this goes 0. So there is there was a lot of activity in the school of Plotkin, in Boris Plotkin in Riga. Also, there are books, one book in Russian, one book in English about this. And if you start again about the non-spective varieties of group representations, there are examples by Gupta and Krasilnikovs. So in characteristic 2, you have two varieties, one satisfying this identity, one satisfying this identity. Here in the square brackets, this is the Lie commutator with usual parentheses. This is the group commutator. And of course, you can speak also about varieties of representations of the algebras. The same statement, but instead of group elements, you take elements from the algebra. And again, in characteristic 2, there is a counterexample. This counterexample is due of Krasilnikov-Shmelkin. If you have an infinite field of characteristic 2, you have this algebra. So you have here upper triangular matrices, zeros in 2 of the places, equal elements here on the diagonal. Here you also have, so this is something 3-dimensional. And this algebra, it has a representation which is 4-dimensional, and it has no finite base of this identity. So this is nice to have examples similar to examples of Krasilnikov and Gupta for group representations for any field of odd characteristic, or of the theorem of Krasilnikov and Shmelkin for infinite fields of odd characteristic. But now I say a couple of words about limit variety. The variety is limit or just non-finitely based if this is not finitely based, and all of its proper subvarieties are finitely based. Of course, by the Zorn lemma, if you have an infinite base variety, it has a limit subvariety. But now I shall discuss some results on explicit examples of limit varieties, which don't depend on the Zorn lemma. For groups, we know that we have limit varieties because Newman, he showed that for any prime p bigger than 2, there is an infinite based variety of p groups. So as a consequence, for each variety you have an infinite, you have a limit subvariety. So the limit varieties are infinitely many. So, but further, it turns out that there are uncountably many limit subvarieties of groups. So this is Kozhevnikov. This is his thesis in Moscow State. And also, there are no explicitly no known examples of varieties, limit varieties of groups. There are examples of varieties which are very close to limit, but they are, up till now, there are no examples. There are examples of so-called bigroups. Bigroups are generalization of integral representations of groups. There are many such results. There are examples for semigroups. They come from the early 80s. And there are more examples by Pollack, by Mark Sapir, by Leon Volkov. And also, it is known that it was by Kleiman that there is a 6-element semigroup which generates a limit varieties of inverse semigroups. And this is the only limit example which is not a limit varieties of groups. So this is something which is, you have 2x2 matrices, which example we already had in some a little bit before. And now the hunting for limit varieties continue also nowadays. You see that there are papers which are even in which are published in 2021, and which are in a peer or which are posted in a peer in archive. So there's a lot of activity still on this problem. For Lie algebras, there is only one example which is known for Lie algebras in characteristic 2. This was done by Volichenko to this central Abelian identity. You added several more identities to get something which is not finitely based. This was in preprint. It was never published in a journal. And if you consider algebra's characteristic 0, it's easy to construct such limit varieties. So they are anti-commutative. The product, they are metabelian in the product of two products of 2 is 0. They satisfy also some other identities. And one can show that this variety is generated by a 6-dimensional algebra with such basis A1, A2, A3, B, C, G, and such non-zero multiplication. And the proof, as in the original proof of the previous one, it used representation theory of the general linear group. And also, you can change a little bit this variety to make it commutative. And again, you have a 6-dimensional algebra we generated. So, if you consider varieties of pairs again, you have a lot of examples due to Isaac Slitin. So I don't want to discuss the proof, but there is a problem which seems to be realistic to find a limit subvariety of the variety which was generated by this algebra here, and to show that to find a limit subvariety. Also, the examples I already gave with finite dimensional algebras which generate limit varieties, they are either commutative or anti-commutative, but it was nice to have such example which is of this kind. And also, it's natural to ask to find limit varieties of algebras in positive characteristic and over finite fields. Of course, you can do the same for associative algebras, for the algebras. And now there is a lot of activity about books which you can read about this. They are by Barturin. Barturin has a new edition of his book, which appeared in a year ago. There are also some survey articles. My book on pure algebras, it has something. There's a paper by Kanebloff and Trowen. Also, there is here Vishne. This is an exposition paper with free access. There is one more paper. So this is, thank you.
I would like to thank you, Professor Drensky, for his valuable talk.